Okay, so good morning everyone. I'm not part of the fusion modeling community. I'm not part of plasma research. I'm a quantum chemist, but just like Klaus, I used to work for 18 months in an experimental group of electron diffraction. So probably that's part of the reason I'm much interested in structural parameters. And I will try to talk about uncertainties of structural parameters. So the word of uncertainty will come up quite a few times during my talk. So the outline is that after a brief introduction and motivation, I will try to define why it's a problem to understand the uncertainty of structural parameters of small or medium-sized molecules. So there is a quantum chemical approach, which I'm rather familiar with. There are empirical and spectroscopic approaches to get structures of molecules. One of the big problems is there are different structural types, so I will try to describe those to you and then talk about uncertainties and we'll try to summarize what I have. So if you are more interested in details about structures, then I recommend this book. This is a textbook which was edited by three of us, Jean de Maison, Jim Boggs, and myself edited this textbook. And for the last 50 years, there have been a so-called Austin Symposium on Molecular Structure organized by Jim Boggs. So he passed away last year, so I would like to dedicate this talk to him. And I will use a lot of material which we either worked on together or I got directly from Jean de Maison. I will acknowledge that. I'm also an expert on force fields, and I will try to show you how force fields come into the picture of understanding uncertainty of molecular structures. So just at the very beginning, what experimentalists and also theoreticians would consider as accurate structures of medium-sized molecules, let's say from 10 to 20 atoms, if the distances would be known to thousandths of an angstrom and the angles to tenth of a degree. So that's like the holy goal of measuring or computing structures of molecules. Now it's, you may realize later on that this goal is not easily achievable, although it is claimed even for diatomic molecules that one can go to 10 to the minus 6 accuracy, one out of 10 to minus 10 to the 6. So there are several sources of uncertainty in structural parameters. One very important one is that the experimental and the first principles, the quantum chemical techniques, will refer to different structural parameters. That's very important. So there are many structural definitions, and of course within each structural definition or measurement or computation, there are intrinsic sources of uncertainties. So let's see, you can use quantum chemistry to compute structures, you can use spectroscopy to determine structures, and you can use diffraction to determine structures. All these red things are things which I will not talk about. So I will not talk about X-ray or neutron diffraction experiments. I will concentrate on gas electron diffraction, so gas phase molecules. Out of spectroscopy, I will not use NMR. I will only use results from rotation spectroscopy. Out of quantum chemistry, I will strictly use wave function-based methods. We will not talk about DFT, too inaccurate. I will not talk about empirical results. And then rotational spectroscopy, quantum chemistry, and electron diffraction will all result in different structures. They all claim to represent the structures of the molecules, but all these structural parameters are different. So how different they are? This is a slide from Jean de Maison, and in gas electron diffraction, the structural parameters which you get out of these experiments are called RA parameters, which are sometimes converted to R alpha T, where T is the temperature. So structural parameters are temperature dependent, as you all know. From spectroscopy, you get rotational constants. I denote them only with B, and 0 refers to the lowest vibrational state. You get vibration, rotation, interaction parameters. Out of these, you can determine so-called RM, which is mass-dependent structures, and you can get also experimental empirical parameters. Out of ab initio computation, if you work within the Born-Oppenheimer approximation, you get equilibrium structural parameters. You can also compute force constants, quadratic, cubic, quartic, and higher order ones. So you can get the RE structure, or if you compute these force constants and you combine them with experimental rotational constants, you get the so-called semi-experimental equilibrium structures. And even now I would say that these are the best structural parameters which you can get for molecules. And of course you would like to compare all these structural results coming from the several different sources and based on several different definitions. Okay. So equilibrium structures, I talked about the Born-Oppenheimer equilibrium structure. This is what you get out from quantum chemistry packages like, say, Gaussian, okay? And since you can use many different levels of theory, basis set, whatever, you can get many, many different REBO parameters. I will get back to this point. There are also the adiabatic equilibrium structures. This is when you would have a mass-dependent potential energy surface and determine the minimum on this mass-dependent potential energy surface. That would lead to the adiabatic equilibrium structure. Semi-experimental equilibrium structures I described, and I will get back to that later. And that, in principle, in gas-electron diffraction, people also try to get experimental equilibrium structures out of experiment. I don't believe that was a really successful attempt. Now, as far as average structures are concerned, which are coming out from experiments, there are many different averages you can make. There are position averages and distance or angle averages. So the position averages have different subscripts. The Z suffix is like an R alpha structure at 0 temperature. You can go with the R alpha structure, which is the average nuclear position. And have a temperature dependence if you are not only considering it at the ground vibrational state, but you try to involve all the other excited vibrational states. There are RG, RA, and many of these averages which you can define. These are all temperature dependent ones. You can define the square of the distance or the inverse square of the distance and so on, and get these structural parameters. There are these mass dependent structures, again, a bunch of symbols, and they are all different, okay? And there are all, empirical structures. These are structures which do not have a well-defined physics. So all these structures have a well-defined physics. They are different, but they are well-defined. But there are some empirical structures, R0, RS, and the RS variant, which do not have a well-defined physics. They are effective or empirical structures. Okay. So accurate structure, yes, please.
In the previous view graph,
yes.
Could you say, for instance, which physical processes is average of R, 1 over R squared taken to the negative of square root?
Right. If you think about the rotational constant of a molecule, then the moment of inertia is mr squared. And then the rotational constant will be 1 over mr squared. So this is how the r to the minus 2 times. And you average that. And when you are interested in r, you have to take that to the minus 1/2 power. Okay?
Of the whole average of 1 over r squared.
Yeah. So accurate structures of gas phase molecules. So especially at this Austin symposia, at the beginning there was always a question, who is better, microwave spectroscopy or gas electron diffraction? Who provides the more accurate structures? So this debate went on for a long time, and then theory came in, and then it meant that experimentalists, now microwave people and gas electron diffractionists, were trying to fight ab initio people, because ab initio people said, oh, we can compute better structures than you can measure. So there was a big debate between experimentalists and theoreticians. And of course, the solution to all this problem is that you should consider both experiment and theory at the same time and use them where they are best and come up with the most accurate structures this way. So why this 1/1000th of an angstrom and 1/10th of a degree? Why we need that high accuracy in structures? Well, the problem is that it's not so much of a problem for angles, but it's for distances. That there is always a very small range of distances which characterize the different bonds. So if you take the CH bond, then the RECH goes from 1.06 to 1.12. So the range is rather small. So if you are interested in the chemistry, so what changes you can see in one molecule compared to the other based on substitutions or whatever, then the range is small, so the variability is small. So you do need accurate structures to understand the chemistry. The same is true for the CO bond, and you can have several other examples to emphasize that you need these highly accurate structures to understand the chemistry. Okay, so this is again a theme which came up several times in different fields, which you are probably more familiar with. So let's take experimental structures. Let's choose a molecule which is benzonitrile, so a CN substitution on the benzene ring. So in the benzene ring, all the angles are 120 degrees. So chemists are interested in, if I introduce this CN group, what will be the change in these angles, okay? So there are measurements shown on this slide, RS, RG, and RM1 structures. These are all measurement results, and this is what they show for this ipso bond angle, which is the change here. So they say 1.82, 1.9, 1.9 with an uncertainty. So you think that everything is well known because they did these experiments, microwave gas electron diffraction experiments, and came up with this ipso bond angle. There are only 12 structural parameters, 10 isotopologues are available, so things look good for this benzonitrile. So you do a computation and you get an REBO structure. I'm not giving you the level of theory at which this structure was obtained. Back in the 80s, when we first studied this molecule, it was Hartree-Fock with a 421G basis set and gave this answer. Now, we didn't believe in that answer. 2 years ago, we repeated the computation at the coupled cluster level with infinite basis set, whatever, and we got basically the same answer. Very different from experiment. Very different from, if you consider the uncertainty in the experiment, okay? Now one can do a semi-experimental equilibrium structure determination, combining experiment and theory, and guess who is right. Not experiment, whatever small the uncertainties were, but theory. Within 1/10 of a degree or so, you can say that this effect is not 1.8 close to 2 degrees, only 0.5 degree. So it's a 400% error on the part of experiment, and less so for the other angles. Okay, so let's talk about quantum chemical determination of equilibrium structures, Born-Oppenheimer and adiabatic equilibrium structures. So quantum theory would be, I do use the Born-Oppenheimer approximation and use high levels of electronic structure theory, either variational or perturbative or quasi-variational like the coupled cluster theory. So first, if you try to study the structure of a molecule, you have to determine how many independent structural parameters this molecule would have. And unlike the force constants, which can go for a simple molecule to 70,000, if you are interested in the 60 force constants, the linear force constants, so the structural parameters, are only a few in relatively simple molecules, so that's good news. Now you still have this zoo of electronic structure techniques, all the way from Hartree-Fock to full CI, small basis set to complete basis set, and so on. And back in the late 1980s, we were really interested in determining the uncertainty of our computed quantum chemical quantities like energies and structures. So we came up with what we called at that time this focal point analysis, and we wanted to get the right result for the right reason. You know, you can have all variants. You get the right, also it happened here before, that you get the right result for the wrong reason. You improve your theory and get away from good experiment. Now we also wanted to add the uncertainties to theoretical predictions. To get the right result for the right reason, you need to consider physical effects, which especially back in the 1980s were not considered routinely, relativistic effects, Born-Oppenheimer, adiabatic corrections, and so on. And we wanted to get really high accuracy so we can move on to spectroscopic application, which was my dream at that time. So what is this focal point analysis approach? You use a family of basis sets, and these basis sets should be built systematically. So this correlation consistent basis set of Dunning is very good. Then you apply these basis sets at different levels of theory. RHF, MP2 coupled cluster, this coupled cluster, that. You include not only valence correlation but core correlation also. You lay out a two-dimensional extrapolation grid out of these results, and then you can see how changes are at different levels of theory by using the correlation increments, not the directly computed results, but the correlation increments. you include these small corrections, core correlation, relativistic DBOC. So to show this picture to you, this is what I call, since Rubik was another Hungarian, the Rubik's cube of electronic structure theory. So you have 3 axes, electron correlation, basis set, these are the 2 which I talked about, but you also have the Hamiltonian. I mean, quantum chemists used to work with just a non-relativistic Hamiltonian. But if you include relativistic effects at different sophistication, then you get different results. So what you would like to do is to move from small basis set, Hartree-Fock, non-relativistic, to the exact answer. Now we know that the exact answer can be, we can give a very precise answer which will still not be very accurate. Experiments still can be slightly different from these results, but at least that's a good goal. So let's see some diatomic paradigms, what it means that we would like to compute structures. So structures are determined, because we are on the Born-Oppenheimer surface, as the first derivative of the energy. Now, on this figure for 2 diatomic molecules, N2 and F2, I show the percent error of the different derivatives with respect to the distance. Okay, and for N2, the first derivative varies very smoothly with the distance. It is 0 where we have the experimental geometry, and the same thing for F2. The higher order derivatives vary a little bit more, but you can get those quite accurately also. But the basic point here is that although if you would do a double zeta basis at Hartree-Fock computation for F2, then your structure, your optimized structure, would be 1.334 angstrom, whereas the experimental structure will be 1.411, a world of a difference, as I described, very, very far away from the accuracy which we would like to arrive at 0.001 angstrom. Why is this so inaccurate when I was saying in the previous figure that even Hartree-Fock theory is doing quite well? Well, the problem is that when you determine your equilibrium structure, then your derivative is 0. But your derivative is a sum of 2 terms, the electronic energy and the nuclear repulsion energy. And one term you can compute exactly, that's the nuclear repulsion term. And the other one is the electronic energy, which you are not computing exactly. How inaccurate you are computing that? You are computing the electronic energy derivative very, very accurately, only with 0.4% error, even at this very, mediocre level of theory. But the problem is that this term is huge, and the other term which you could compute exactly if you knew where to compute, that's also a very large term, but with an opposite sign. You cancel 2 huge terms, so you move away from the true answer very easily if you do your computation at the Hartree-Fock level. Okay, it is even more clear for higher derivatives. The force constant is 8.8, the true force constant is 4.7. But if you would do the computation at the experimental geometry, you would realize that, oh, my second derivative of the energy is just as good as my first and third and fourth and so on. The only problem is this cancellation of the 2 terms. So if we move up in the level of theory, we can do extremely accurate computations. So let's move up to almost full CI, or almost full basis set, and then we compute the equilibrium bond distance, OH in H260 and the angle. And we can add corrections to that. So if we move from this basis set to the complete basis set limit, the difference is very small. Relativity fact, it's there, but only in the 4th digit. Core correlation is very important. You need to consider all the electrons. Quantum electrodynamic effect is basically negligible, even if you are interested in highly accurate parameters. Diagonal Born-Oppenheimer is pretty good. So you can come up with an estimate of the best possible equilibrium structure of water based on these ab initio computations. And these results are probably more accurate than what you can get experimentally. Okay, so what can you get experimentally? For example, you can get RM, mass-dependent structures. Since this is the worst possible approach in my eyes to add highly accurate structural parameters, I only have one slide. here. So all these empirical structures are based on the fact that the equilibrium inertia is different from the zeroth order, the lowest vibrational state, by a quantity called epsilon. And this epsilon can be taken zero, constant, or you can have a complicated dependence. And depending on how you treat that, you get all these different structural parameters. Okay, and then you can do a least squares fit, or you use non-least squares fit. And there are famous people working on this problem and coming up with these structures. But the best approach is to use the semi-experimental approach, which was pioneered by Peter Pulai, Wilfried Meyer, and Jim Buggs. And this is really the approach where you combine experiment and theory. There can be two approaches in this combination. So you can move either from experiment, where you have this BV, vibration-dependent rotational constant, which would connect to the equilibrium constant, and then a Taylor series expansion. If you take only the first order term in V plus 1/2, then you get these alpha vibration rotational constants, and then there could be other terms in this expansion, but the simplest approach is to use these alphas. Experimentally, you get these B zeros. It's almost impossible to get these alphas, so you get them from theory for the semi-experimental approach. Now, from the theoretical point of view, you can make an inverse procedure, and you can determine a hypersurface, get the equilibrium geometry, and then you do variationally the averages and try to come up with these BV constants if you are within the usual approach and you use the Eckart embedding. So in another slide, the equilibrium rotational constant is almost equal to the measure B0 constant plus the sum of these alpha terms, which can come from different sources, experimental theory. There are only 3 rotational constants. If you have planar molecule, only 2. So you need several isotopal molecules, isotopic substitutions, and that's rather hard to do experimentally. So what do we do in this semi-experimental equilibrium structure approach? From spectroscopy, we get the B0 constants, and from ab initio force field computations, we determine these alpha I constants and combine the two, and then get the BE, the equilibrium rotational constants, and do a fit of structural parameters and determine the best equilibrium structural parameters of the molecules. Well, the advantage of this approach is that this epsilon, which I told you, which is the B0 minus BE, that it is small, less than 1% of the rotational constant. So high accuracy is not that much needed for this correction, but it's good to have. It's relatively easy for the isotopologues, and it is fast once you can compute hundreds of thousands of force constants easily. It's that easy that it can be applied to large molecules, even to amino acids, so we determine the equilibrium structures of amino acids. But there are problems with this approach. One problem is that the accuracy of the ground state rotational constants must be high. Now you would think that since these ground state rotational constants come from experiment, they are highly accurate. Unfortunately, you need even higher accuracy than what's available in some cases, when they could measure only relatively few lines for substituted isotopologues. So these substituted isotopologues is maybe not that easy to make and do the measurement. And there are small coordinates which are also disadvantageous for this approach. So if you are close to one of the principal axes, then that's a problem. And the principal axis rotates, and if it rotates a large amount, then that's also a problem for this technique, and it can happen for certain tops, as shown here, and there can be also this ill conditioning problem during the fitting. So how inaccurate these rotational constants can be? So we determine the highly accurate. This is with the chairman. We determine the highly accurate potential energy surface mass dependent for water. Use that for D216O, and we compare A and B rotational constants for different vibrational states between experiment and theory. Now we knew that our surface is so accurate that we should have a difference between our variational rotational constants and experiment constants down to 10 to the minus 3 or so in centimeter minus 1. much larger deviations were observed. We didn't know what to do. Experimentals saw this paper and came up with a second experimental set of rotational constants. And see, the agreement is orders of magnitude better. So that's a lesson that even rotational constants can be inaccurate. I mean, they show the quality of the data, but these are effective constants, so they can be wrong as well. So you have to be careful. And this is the expected agreement between our variational results and the experimental results. Okay, so this rotation, I don't have time to deal with, but I would like to show another slide where I show that even for simple linear molecule HCO+, there have been in the literature, so from 88, experimental determination of, say, the CH and the CO bond length. And uncertainties attached, experimental, people have to attach uncertainties to their quantities, and 6-digit accuracy. Ab initio results, again, you can attach uncertainties, but very, very different, from experiment. Who is right and who is wrong? Of course, if there is a careful ab initio investigation and a careful determination of the uncertainty, this has to be right. So there have been other ab initio and then semi-experimental structural determinations clearly showing that not within this uncertainty, but with a large extent, this experimental study was just plain incorrect for this molecule. So back to the question of different structural types, what it means that, and this is back to that question, that you have to have different averages depending on the experiment you do. Some of these averages will be more appropriate, and in some cases less appropriate. This average is appropriate for electron diffraction. This average is appropriate for microwave spectroscopy. And the R⁻³ would be for NMI dipolar couplings. And these different techniques will yield rather different bond length. So the R0 and the RZ and RE and whatever, they cannot be compared. It would be like, although these are all structural parameters, this would be like comparing apples and oranges. You can compare two R0 structures, they will be different, two RZ and whatever, but they all would be different. So the best, I think, these days is to go to the equilibrium structure that's relatively well defined. And this semi-experimental equilibrium structure is probably the best what's available these days. Even for simple molecules like cyclopropane, you see the variation in the results. And so this variation is quite characteristic between RE and other like RS and R0 structures. Of course, sometimes even within the same method, RE structures can be different, but at least you know what to do, how to push the level of theory to convergence, which was also the theme of the previous talk. So some examples about structures. So one question is, I was talking about isotope-dependent potential energy surfaces, isotope-dependent structural parameters. Now most chemists would learn that the OH bond length is different from the OD bond length. Okay, that's sort of known. Now this is just half of the truth. There is basically no difference between an OH and an OD bond length if you compare equilibrium structures. But if you compare effective structures in the first vibrational state, yes, there is a difference because it's an enharmonic potential. So equilibrium structures are good in this sense also that there is basically no isotopologue effect, not even in the angle. Back to this problem. So was this also true that experimental theory is different for benzonitrile? No, the same is for phenylacetylene. Here even the two experiments differ, and again they are much different from the well-converged theoretical result. So the problem with experimental uncertainties is ubiquitous. Okay, so how to determine the experimental uncertainty when you when you determine this semi-experimental equilibrium structure of molecules? Well, it's a problem. One problem is that the degrees of freedom is large, so in the fitting process that's a problem. Isotopic substitution is sometimes impossible, for example for fluorine, or not available because it would be too expensive to make that molecule and get the measurement of B0. The errors are not always systematic in BE. If the errors are systematic through the fitting, you can get rid of this error. If the error is not systematic, that's a problem. The expansion, when you include only alpha and not the high-order terms, that's a problem. The first high-order term is the so-called gamma term. Electron correlation resonances, that all will affect these constants. Whether the errors are independent or not, that's a problem. The condition number of the fitting may be large, which means that you have a problem in the fitting, so you have to work on that. And of course, there is always a problem with the weight you use in these fitting procedures. Now I'm sort of running out of time, so I would like to emphasize only a solution to the fitting problem, which is used in the community of electron diffractionists and these spectroscopists who are trying to do highly accurate structure determination, and it's the use of predicate observations. I haven't heard that here, so this is a very good thing to do. In the least squares refinement, you have weight factors, and you compare the experimental and the calculated results, but you also use computed results with different weight factors. So if you know your computed result should be correct within this amount, that during the least squares refinement you would not like to move too far away from your predicted calculated structural parameters, and you can include that in the least squares fit. And this predicate observation, this goes back to the 70s or so, and to an electron diffractionist, as far as I know. It is a much better procedure to make sure that you end up with the correct structure. Now I would like to do about one more thing, how to unify data coming from the different sources. So this part of the talk will show to you that, again, just for the simplest molecules, let's say for H2O, you can really go from Born-Oppenheimer equilibrium structures to experimentally measurable structures. So if you have the equilibrium structure, let's say adiabatic equilibrium structure, you can do some averaging and can come up with RG parameters at any temperature for any isotopic substitution. You see how large the difference between equilibrium and effective parameters are for the bond lengths and the bond angles. And the way you do it, you take these averages, maybe the R average or the 1/R average, and then you get to RG, temperature dependent parameters using these Boltzmann factors. So this is a straightforward computation once you have the structure and the ability to solve the nuclear motion problem. And then you can come up with RG calculated structures, RA calculated structure, and you can compare those effective structures to the structures coming out of experiment. So the difference between gas electron diffraction and calculation is not large. If I would have added the uncertainty what the gas electron diffraction people added to this, that would be 2 × 10⁻³ so they were correct. But we can come up with any kind of structural parameters, and there are some perturbative results which can be used and make sure that those are also a correct representation of the problem. Now, to do this averaging, you not only need to consider vibrational averaging, but the full row vibrational averaging. So that's a rather expensive thing. The good thing is that if you do the rotational part, then the temperature dependence is perfectly linear, so you need to do only a few J's, you get the slope of this, and then you extrapolate in temperature, and you can come up with structural parameters at any temperature, in principle for a simple molecule for which you have a highly accurate potential energy surface. So you can compute other parameters, you can extend this to ammonia, so it's not only water, ammonia is also possible, and shows that those who were interested in these fundamental questions in the gas electron diffraction community, they did come up with correct RG and RA estimates. Now our computations prove that. And I would like to summarize in a few words what I tried to show you. and that is that the very accurate molecular structures can be obtained if you combine experiment and theory. Probably you are better off doing theoretical computations first and at a very as high level as possible, but you need to include experiment to make sure that the results are correct. And if you try to compare the different methods, first principles, quantum chemical, experiment, and semi-experimental, then the difficulty level is for first principles, I say difficult. If you did only use Gaussian and couple cluster, just the Born-Oppenheimer, then it's easy. The difficult part is to include the nuclear motion in getting the structure. Experiment is difficult, semi-experimental is rather easy. The speed, this first principle is slow, experimental is slow, semi-experimental rather fast. The price, expensive, rather cheap, so that's why this is the best solution. And as far as uncertainties go, it's rather difficult still to estimate the correct uncertainty of your obtained structural parameters. And with this, I would like to close my talk, and probably the coffee break is coming up soon.